Okay, well, ice tables haven't killed us yet, so let's keep going. 2 carbon monoxide, they say, plus oxygen. At this point, honestly, I haven't even read the question yet. I just know we're in the ice table section, so I'm going to set up a table right away because in my peripheral vision, I can see a bunch of concentrations coming at us, and we need a place to store those. So away we go. 2 carbon monoxide and an oxygen can convert into 2 carbon dioxide. And we're going to track the usual stuff, initial, change, and equilibrium amounts. Okay, what are they giving us? Oxygen and carbon monoxide are mixed and allowed to react. All they're giving us is the change, it looks like. They're saying there's oxygen and carbon monoxide, but we have no idea how much. And we might be able to assume there's no carbon dioxide at first. And they tell us the oxygen goes down by 0.03. I don't always bother putting minuses on these, but I will with this one just to help us keep track as we don't have a lot of other information to work with. Well, look at the ratios. The ratio of oxygen to carbon monoxide is 1 to 2. There's always twice as much carbon monoxide. So if you lose 0.03 of oxygen, you must be losing twice that much carbon monoxide. And the dioxide number, there's two ways you could do this. You could say the oxygen number doubled is your carbon dioxide. Whatever this is, the CO2 is twice as much. Or you could say the carbon monoxide and the CO2, because they're 2 to 2, those numbers always match. So if one of them is 0.06, the other one must be 0.06 also. And that's actually all they want. They say, how much did CO and CO2 change? The CO fell by 0.06 moles per liter, and the CO2 increased by 0.06 moles per liter. We couldn't get equilibrium amounts because we don't know what the initial amounts were, but we can at least do this because this is just dependent on the coefficients. We only needed one number here to get us started, and we can tear around and find this entire row. Okay, what have we here? Phosphorus trichloride. Let's write this out. Phosphorus pentachloride. Initial, change, equilibrium. Okay, what have we got? 0.2 moles of PCl3. Can we put this in the table? We shouldn't automatically put this in the table because it's just moles. However, something nice happens. The concentration is number of moles divided by volume. So it's 0.20 moles divided by, what's the volume? Hooray, 1 liter. So that means we can use these numbers because we're dividing them all by 1. PCl3 is 0.20. Chlorine is 0.10. They say those things were put in a flask. Probably there was no PCl5 in the flask at first, so we'll leave that as 0. And so they put those amounts in the container, and then they go for lunch, and when they come back, they find the flask contained 0.12 moles of PCl3. 0.12. Okay, so, and from all that, they want us to find the equilibrium constant. Let's get that out of the way before we dig in. The equilibrium constant is products over reactants, so it should be PCl5 pickle 5 over pickle 3 times chlorine. All of these had coefficients of 1, so the powers here are all 1. And yeah, right now we only know one of these numbers, so clearly we're not ready to dig into the K yet. Let's see if we can tear around this table and find some things. Where do you think we should start? Anytime you have a column where you know 2 of the numbers, that's probably a good place to dig in first. We can find this change amount. If we started with 0.20 and we ended up at 0.12, that means there was a total loss of 0.08 for the phosphorus trichloride. Now, this is nice. Because these all have coefficients of 1, that means the amounts of them that react are always going to be the same. So 0.08, 0.08. A 1 to 1 to 1 ratio means these numbers are always identical, which is nice. So here we had 0.20, we lost 0.08, we're down to 0.12. Here we had 0.10, we lost 0.08, now we should be down to 0.02. And on this side, we started out broke, we created 0.08 of phosphorus pentachloride, so we should be up to there. And that means we should have everything we need to find an equilibrium constant. Remember, equilibrium constants, KEQ, when we're writing them up in detail, can only be found from equilibrium numbers. If you use these or these, you will be sorry. K only holds for the equilibrium values. So PCl5, 0.08, PCl3, 0.12, chlorine, 0.02, and 0.08 divided by 0.12 divided by 0.02. I get 33.3. How many sig digs are we looking at here? 2, 2. Yeah, everything's 2, so 33, I guess. We don't have enough precision to give us any decimal places, so K is about 33. Okay, HBr reaction again. I think we've seen this one. That's okay. 2HBr can turn into hydrogen and bromine. Initial change equilibrium. And we've got 0.5 moles of HBr in a 1 liter container, so yay, 0.5 divided by 1 is still 0.5. So they put HBr in the container, and apparently that's it. So there was no hydrogen and there was no bromine when this started off. And then they just leave it and let it sit there for a few hours and let it decompose. And at equilibrium, bromine is measured to be 0.13 moles per liter. And they want a K. Let's set up the K again just to get it done. Hydrogen to the first power. Bromine to the first power. Hydrogen bromide to the second power. Okay, right now we only have one of those numbers, so let's get to work. What can we find? This is good. We started with no bromine. We ended up with 0.13 of bromine, so apparently we created 0.13 of it. Hydrogen and bromine are in 1-to-1 ratio, meaning these numbers always match. So if we made 0.13 of bromine, automatically we made 0.13 of hydrogen as well. The HBr, though, is twice as big as either one of these. This is 1 to 1 to 2, so this number, same number, twice as much is what should go there. So for equilibrium, we had no hydrogen. We made 0.13 of hydrogen, so that's our new amount. We started with 0.5 of HBr. We used up 0.26. We must be down to 0.24 because we're using up reactants, we assume, and making products. These numbers are going down, going up, getting added because we're creating these two species. We're subtracting on this side because we're using up HBr. So now that we have these equilibrium numbers, we can probably math up a K here. I was going to say magic up a K, but it's not magic, it's math. Hydrogen is 0.13. Bromine's 0.13. If you wrote 0.13 squared, great, good idea. I kind of wish I'd done that. And HBr is 0.24 squared. So out comes the calculator. 0.13 squared divided by 0.24 squared. And I get 0.2934. Now, how much of that are we actually keeping? 3 sig digs, 3 sig digs, everything's 3 sig digs, so 0.293 is where we should stop. That's more like it. All right.